In June 2015, the air over Karachi, Pakistan, moved into territory scientists had long treated as nearly unreachable. For about 1 day in every 10, heat and humidity joined in a way that left an older human body with no reliable path to cool itself. Within 10 days, at least 1,200 people were dead. That boundary, the real edge of human survival, is the quiet subject before us. What makes it so disturbing is not simply that Karachi touched it, but that a warming world may be pushing that same threshold towards some of the most densely populated regions on Earth, including a large portion of the United States. So in this calm space journey, we will move carefully through a dangerous question: why moist heat can be far more lethal than dry heat, where the survival limit truly lies, and what might unfold if it arrives in a major city just as the power grid gives way. It is a story about weather, but also about the fragile machinery of the human body. And the closer we look, the less ordinary a hot summer afternoon may seem. First, we need to understand the line you do not necessarily feel approaching. There is a point at which even a healthy person, resting motionless in deep shade with endless cold water available, will still die. Not because they are thirsty, not because sunlight is burning their skin, and not because danger is visible in the usual ways. The body simply loses the ability to perform the cooling process that has allowed humans to survive hot environments for hundreds of thousands of years. Once that system fails, time begins to matter in a different way, and the person can no longer solve the problem by instinct. That may sound like the premise of a disaster film, and it is natural to resist it as dramatic language. Yet this is not spectacle. It is physiology. It is among the quieter, more firmly understood truths in environmental science. The reason it has not often been spoken about so plainly is that, until recently, the conditions needed to pass this boundary almost never appeared on Earth. They lived mostly as a theoretical mark on a chart, a limit people studied without expecting cities to meet it. Now that assumption is becoming harder to hold. The unsettling part is not merely that such a limit exists, but where it appears to sit, and how quickly a warming planet could carry crowded places toward it. Before going further, pause on the image most of us associate with deadly heat. Many people imagine desert ground split by dryness, air wavering above pavement, and a thermometer showing a brutal number in Phoenix or Death Valley. Those places can indeed become dangerously, even lethally, hot. But the great twist is this: many of the worst modern heat disasters have been dry heat events, and by the survival measure that matters most, they did not reach the true physiological ceiling we are examining here. Tens of thousands have died in heat waves that researchers would still classify, in this specific sense, as survivable heat. That idea can be difficult to absorb, because it rearranges the whole mental map of danger. Heat has already killed more people than any other weather disaster in the United States and across much of the world. Yet even those events do not represent the most severe heat the human body could face. Above them is another category, one so rare in the historical record that we have only seen it graze a major city a few times. And that category is no longer standing still. Researchers who spend their careers studying this threat often describe it with unusual bluntness. In effect, they warn that beyond a certain threshold, breeze does not rescue you, shade does not rescue you, and drinking water does not rescue you. Those are the natural defenses we reach for, and in most heat they matter enormously. But past the critical point, the body's cooling mechanism itself has stopped working. A person can make every sensible choice and still begin to overheat from within. These are extreme humid heat events, and climate modelers often treat them as one of the most alarming consequences of a warming climate. Their danger is not cinematic. A wet bulb disaster does not announce itself like a wildfire, nor does it arrive with the visible violence of a hurricane. It can resemble a heavy, sticky afternoon that refuses to release its grip. Then, Inside houses, apartments, and care facilities, people who cannot shed heat begin to lose the ability to compensate. This kind of catastrophe may hide inside weather that looks almost familiar, which is precisely why it deserves careful attention. So, for this calm space episode, the path is different from a storm chase across a satellite map. We are going to take apart what may be the most dangerous weather threat humans face and follow it down to the number where survival ends. We will look at why humid heat can be more deadly than dry heat, even when an ordinary thermometer shows a lower reading. We will examine the experiment scientists carried out on real human bodies to identify the true limit and why the result was lower and more troubling than the textbook value used for years. From there, we will consider where on Earth this boundary is projected to be crossed. One of the more sobering details is that part of the answer is not a faraway tropical shoreline, but the eastern United States. Finally, we will turn to the one protective tool many people rely on, the machine humming in a window, a wall, or somewhere nearby. Air conditioning is our strongest defense, yet in a way many rarely stop to consider. It is also connected to the problem it helps us survive. That tension matters, because it suggests that protection and vulnerability may be more tightly linked than they first appear. To understand the survival line itself, we first have to understand how the body remains alive in heat at all. Once the engine is clear, the failure becomes much easier to see. At this moment, your body is producing heat, and you cannot simply decide to stop. Every cell is using fuel, and warmth is released as a byproduct, much as an engine gives off heat while it runs. Even while sitting calmly, you generate roughly as much heat as an old incandescent light bulb, around 100 W. Stand up, move around, or work, and that figure rises quickly. Deep inside you, where the vital organs are, the core temperature has to stay within a narrow range, near 37 degrees or 98.6 degrees F. Raise that internal temperature by only a few degrees, and the situation becomes serious. Raise it far enough, and the proteins that keep the body functioning begin to fail. In this sense, your body is always balancing an invisible ledger, heat entering, heat leaving. On a cool day, the math is simple, because the surrounding air is colder than you are. Heat usually leaves the body quietly, passing from warm skin into cooler air, much like warmth drifting away from a hot cup in a cold room. On a scorching day, though, that simple escape route can disappear. If the air around you is warmer than your skin, your body can no longer unload heat in the usual way. If the air becomes hotter than the body itself, heat may even begin moving inward. At that point, human survival depends on a backup system so ordinary that we often forget how remarkable it is: sweat. This is where the story turns from comfort to physiology, and the question becomes not merely how hot the day feels, but whether the body can still defend its inner temperature. Sweating may be one of the least celebrated abilities in the animal kingdom, because most of the time we notice it only when it dampens clothing or makes us uncomfortable. Yet the human version of this process is an evolutionary achievement of extraordinary importance. It helped our ancestors keep moving through the open heat of the African savanna, even when many other large animals had to retreat into shade and wait for evening coolness. The mechanism is simple, but its simplicity is exactly what makes it elegant. When water shifts from liquid to vapor, it must take in energy. The forces holding liquid water together do not separate for free. They require a large input of heat. When sweat on your skin evaporates, that energy is drawn from you. The departing water molecules carry heat away. Your skin temperature drops. The blood moving just beneath the surface cools as well, and that cooler blood returns inward toward the core. In effect, your skin becomes a living radiator, using water as the working fluid. A small breeze feels wonderful when you are hot and damp, because moving air clears away the moist layer clinging to your skin and replaces it with fresher, drier air that can take up more water vapor. The same principle explains why, after leaving a swimming pool on a windy day, you may shiver even in warm air. Water is vanishing from your skin rapidly, and the heat needed for that vanishing act is being taken from your body. This quiet exchange is one of the body's great balancing acts, and it may be easy to miss precisely because it works so well. Humans are built with roughly 2 to 4 million sweat glands, and in extreme conditions, a well-adapted person can release 1 to 2 L of sweat in an hour, with even higher output for brief periods. That is a tremendous potential for cooling. It helps explain how a person can endure a desert afternoon that would be deadly for many other mammals, provided two conditions remain true. The lost water must be replaced, and the surrounding air must be able to receive the moisture being pushed out of the body. Hidden inside that second condition is the danger. Sweat only protects you if the air will let it become vapor. Evaporation is not simply something your body commands. It is more like a bargain between wet skin and the atmosphere immediately around it. Dry air behaves almost like it is hungry for moisture, drawing water away from the skin quickly and making the cooling effect strong. But air has a limit. Once it is close to saturation, already holding about as much water vapor as it can, it has little capacity left for yours. Sweat can still stream from the glands, cover the skin, soak fabric, and run down the back. But if it does not evaporate, it provides almost no cooling. The cooling does not come from sweat appearing. It comes from sweat changing state. Without evaporation, the water is mostly lost effort. This is the crucial divide between dry heat and humid heat, and it can mark the boundary between misery and danger. In dry heat, the body's radiator can operate with great force. In humid heat, that radiator may be restricted, weakened, or in severe cases nearly disabled, just when the body most urgently needs it. This distinction matters because our senses can be misleading. Many people have known a very hot, dry day, with temperatures reaching well into the 9s or higher, that still felt strangely manageable in shade, especially with some wind. In that setting, sweat may disappear almost as quickly as it forms, so quickly that you may hardly register how much work your body is doing. The system is under strain, but it can still succeed. By contrast, a day in the ATS can feel far more oppressive if the air is saturated with moisture. The air seems heavy and wet, almost like breathing through a warm towel. Within minutes outdoors, clothing may be soaked, and the sweat refuses to dry. For the body, that lower temperature day can be more threatening than the hotter, dry one. The thermometer, by itself, leaves out the essential part of the story. What matters is the combination, the temperature of the air and the amount of moisture it is already carrying. Together, those two values determine whether the body's cooling engine can keep running. For much of human history, this difference was important but not usually catastrophic, because the most perilous pairing, very high heat joined with very high humidity, was uncommon. It required a particular setup, a nearby ocean or a flooded landscape supplying moisture to the air, plus enough heat to push that damp air toward the edge of what the human body can tolerate. A few regions on Earth could produce such conditions now and then, perhaps for an hour or two during the harshest part of the harshest days, but it remained exceptional. The great heat disasters that killed people and filled morgues were usually dominated by dry heat, often under vast stalled domes of high pressure that baked whole continents. To understand why the future may carry a more severe threat, it helps to begin with those dry heat catastrophes, because they form the baseline. They are the deadliest heat events in the record, and yet, for all the suffering they caused, they generally remained short of the deeper physiological boundary. One number helps reveal how powerful the human cooling system can be when conditions allow it to function. In severe circumstances, a well-adapted person may lose a liter or two of sweat in just 1 hour, and briefly, sometimes more. Each liter that evaporates removes a very large amount of heat, far more than intuition might suggest, because converting liquid water into vapor demands so much energy. That is the scale of the cooling engine every human carries through the world. Quiet most of the time, but essential when the air turns hostile. Human beings can keep moving in desert heat that would send many large animals searching for shade and stillness. In that sense, we are built for endurance under hot conditions, and the sweat gland is the quiet mechanism that makes this possible. Yet this advantage rests on a delicate requirement, one that is easy to overlook. Sweat does not cool the body simply by appearing on the skin. The cooling happens when that liquid escapes into the air as vapor. A body can release water continuously. But if the surrounding air will not let that water evaporate, the sweat only runs off, taking fluids and salts with it. The whole remarkable system depends on evaporation, and evaporation depends on air that can still take in moisture. Once the air is already loaded with water, that pathway begins to close. However hard the glands keep working, the animal kingdom's most impressive cooling apparatus has a single weakness, and humid heat can exploit it. Before we reach the point where that weakness becomes fatal, though, we need to pause with another kind of danger, heat that does not rely on humidity at all. This is the dry heat that has caused so much death in human history, the heat of the Great Domes. In the summer of 2003, a huge body of hot air settled over Western Europe and stayed there. The disaster that followed was not an accident of a few warm afternoons. It came from one of the atmosphere's most persistent and powerful patterns. A heat dome. The process begins when a broad zone of high pressure locks itself over a region. Inside that system, air descends from above toward the ground. As it moves lower, the pressure around it increases, compressing the air, and compressed gas warms. This warming does not come directly from sunlight. It is produced by compression itself, a process known as adiabatic heating. The same principle can be felt when a bicycle pump grows warm as the plunger is forced downward. Day after day, the sinking air heats as it compresses. At the same time, high pressure tends to strip clouds from the sky and quiet the winds, leaving little to move the heat elsewhere. Sunlight falls through clear air onto land that grows hotter, and the ground gives that heat back. Nights fail to reset the system. Each morning begins from a warmer starting point, and the dome becomes a slow, sealed oven. As long as the high pressure remains fixed, the cooking continues. This is why such events can feel almost invisible at first, like weather merely refusing to change, until the human cost begins to appear. Europe in 2003 was not prepared for a heat structure of that scale. In many countries, home air conditioning was uncommon because the climate had not usually demanded it. Cities of stone and brick absorbed heat through the day and released it after sunset, weakening the relief that night might have offered. Many older people lived alone. Temperatures climbed beyond 40 degrees C, over 104 degrees F, in places where numbers like that had rarely belonged to normal experience. Still, the dome held. When the losses were later counted, the estimated death toll across Europe was around 70,000 people. In France alone, roughly 15,000 people died, many elderly, many in urban settings, and many during a harsh period in August, when much of the country was on holiday and the heat found it unready. Paris was among the worst affected places on the continent. The 2003 heatwave remains one of modern Europe's deadliest natural disasters, though beyond Europe it is not remembered as widely as many events with lower death tolls. Perhaps that is because it left no single dramatic image, no wall marked by floodwater, no town flattened in an instant. There was only a long, punishing heat, and then the quiet count of those who did not make it through. The same pattern did not end there. During the summer of 2010, a still more intense heat dome formed over western Russia. Moscow endured temperatures it had never recorded before. Peat bogs and forests burned, and smoke enclosed the city, trapping people between dangerous heat outside and contaminated air around them. The estimated death toll from that event reached around 55,000 people. The heat also destroyed roughly a quarter of the country's grain harvest, sending shocks through global food prices. Once again, the structure was a dry heat dome. Once again, the loss of life reached into the tens of thousands. These episodes suggest how a weather pattern can become a societal stress test, exposing what buildings, routines, and public systems quietly assume about the climate around them. Then came an event much closer to home, one that should have unsettled assumptions about where lethal heat can occur. In late June of 2021, a heat dome of extraordinary intensity developed over the Pacific Northwest of the United States and Western Canada. This region is known for its mild, cool, green character, evergreen forests, ocean fog, and summers that had long seemed gentle enough that many homes did not have air conditioning. The dome ignored those expectations. Records were not broken by small margins, they were shattered by staggering ones. In the small town of Lytton in British Columbia, the temperature reached 49.6 degrees C, or 121 degrees F. It was the hottest temperature ever recorded anywhere in Canada, a country many people associate with cold and snow. The next day, after setting that record, the town burned to the ground in a wildfire. Scientists who later examined the 2021 Northwest event reached a conclusion that is difficult to absorb calmly. Under the climate of the time, they assessed it as something like a 1-inch 10,000-year event, an extreme outlier at the edge of what their models considered possible. More than 1,000 people are estimated to have died across the region from that single heatwave, in a place not known for extreme heat, and in homes built around the expectation that such heat would not arrive. And yet, this is the turn that matters for the larger story. However devastating these three disasters were, and however far they pushed beyond local history, none of them reached the true physiological boundary we are moving toward. Europe in 2003, Russia in 2010, and the Pacific Northwest in 2021 were all, at their core, dry heat events. The air was brutally hot, but it was not saturated with moisture. Human cooling systems were under severe strain, especially among older people, the sick, and those without access to cooling, but evaporation had not been fully taken away. That distinction may sound small, but it opens the next and darker question. What happens when the air is not only hot, but so wet that the body's last defense begins to fail? Yet, in that dry furnace, the body's cooling machinery had not failed in the deepest physical sense. With enough water, stillness, and time, a healthy person could still move heat out. That is the crucial threshold to keep in view. If dry air, at 121 degrees, heat severe enough to kill thousands, can remain just barely on the survivable side, then the question becomes darker. What lies beyond it? What form of heat is so unforgiving that shade, drinking water, and even moving air may no longer be enough? To find that boundary, we have to return to the familiar misery of a damp shirt sticking to your back on a humid afternoon, and to a deceptively simple instrument, a thermometer with a wet cloth fitted over its end. That small device helps reveal how near any given day may be to the limit of human survival. The question matters because heat does not only attack through spectacle. Often, it works quietly, over hours and nights, until the body has no interval left in which to recover. This is why a heat dome can become such an efficient killer, and why its danger is so easy to underestimate even in wealthy modern regions. The most important threat is not always the peak temperature at the hottest moment of the day. More often, it is the build-up. In ordinary heat, nighttime brings a kind of reset. The air cools, the body unloads some of the heat it carried through the afternoon, and by morning it has a chance to begin again. Under a heat dome, that release may never arrive. The same sinking, trapped air that intensifies the daytime heat also keeps warmth sealed in after sunset, so the overnight low remains too high to provide real relief. The body enters the next morning still burdened, already carrying a heat debt it could not shed. Across several days, that debt can accumulate until those with the least reserve are overwhelmed. This helps explain why deaths during heat waves often rise most sharply on the 3rd, 4th, and 5th days rather than at the very beginning. It is less like a sudden strike than a slow encirclement. And there is another reason these systems are becoming more dangerous, one that brings us closer to the boundary we are tracing. A heat dome forming over a warmer planet begins from a warmer starting point. The atmospheric pattern may be familiar, but the air available to it has shifted upward. In that sense, the floor beneath each event has been raised, allowing similar domes to reach further into record territory than they would have a few decades ago. The dry heat catastrophes of the past, as terrible as they were, may be only the milder warning. They show that heat can kill long before the wet bulb limit is reached. The more troubling question is, what happens when a dome settles over air humid enough to push conditions beyond that line altogether? For that, one measurement is needed, because it captures both parts of the danger at once. Here, the story turns to the sock, the sweat, and the number 35. Scientists describe the survival edge with a term that sounds unusual, but is almost literal: wet bulb temperature. The name comes from one of the simplest ways to measure it. Start with a standard thermometer, the kind that records the actual temperature of the air, known as the dry bulb temperature. Then cover the bulb at the bottom with a small piece of wet cloth, a wick, or something like a tiny sock, and keep that cloth supplied with water. Expose it to moving air, and a quiet demonstration begins. Water leaves the cloth through evaporation, and as it does, it carries heat away from the thermometer, just as evaporating sweat carries heat away from skin. Because of that cooling, the wet bulb reading usually falls below the reading on the ordinary thermometer beside it. In miniature, the instrument is reenacting the same process your body depends on. That is why such a simple setup can point towards such a serious limit. It turns the feeling of oppressive humidity into a physical number. The size of that difference depends on how much moisture the air can still accept. In very dry conditions, water evaporates rapidly from the cloth, cooling is strong, and the wet bulb thermometer can register far below the actual air temperature. In humid air, the effect weakens. The atmosphere is already holding a great deal of water vapor. Evaporation slows, and the wet bulb number rises closer to the dry bulb temperature. If the air becomes fully saturated, so that no additional evaporation can occur, the two readings meet. The wet bulb temperature and the air temperature become identical. This is the key to why the measurement is so important for survival. The wet cloth functions as a stand-in for sweating skin. It is a rough physical model of the body's evaporative cooling system. A low wet bulb temperature suggests sweat can still evaporate effectively, allowing the body to release heat. A high wet bulb temperature means that system is failing. And if the wet bulb value climbs to the level of human skin temperature, the air is both hot and saturated enough that evaporation can no longer remove heat in the needed way. There is too little temperature difference and too little room left in the air for sweat to become vapor. At that point, the body is no longer negotiating successfully with physics. This is why scientists watch the wet bulb number, not merely the temperature glowing on a sign outside a bank. It combines heat and humidity into one more honest measure, asking a direct and unsettling question: can a human body continue to cool itself in this air? For many years, the textbook answer placed the outer survival boundary at one clean figure: 35 degrees C wet bulb. In Fahrenheit, that is 95 degrees F. But as a wet bulb reading, it means something far more dangerous than 95 degrees on an ordinary thermometer. The reasoning behind the number was simple and, at first glance, persuasive. When a person is sweating hard, skin temperature is roughly 35 degrees C. If the surrounding air also reaches a wet bulb temperature of 35 degrees C, then the gradient that allows heat to move away from the skin disappears. Even a person at complete rest could no longer cool themselves naked in the shade in front of a fan with unlimited water available. The body would continue producing metabolic heat, but the usual escape route would be closed. Core temperature would rise, and within hours, hypothermia could become fatal. The number is stark because it is not about discomfort. It describes a condition in which the body's normal strategy for survival may no longer work. That 35 degrees C threshold emerged from foundational scientific work, especially a 2010 study by Stephen Sherwood and Matthew Huber. Their finding contained a detail that can sound almost comforting at first. In the present climate, they noted, wet bulb temperatures across the planet essentially never rise above about 31 degrees anywhere, even in the most punishing humid heat of the Persian Gulf and South Asia. The worst air conditions, then observed, remained several degrees below the theoretical, fatal boundary. But that gap is also what makes the measurement so haunting. It suggests that the danger is not merely the temperature we see, but the shrinking margin between what the body can endure and what the atmosphere can impose. For most of human history, there has been a hidden safety margin between the most oppressive humid heat Earth can create and the point where the human body can no longer keep itself alive. Early calculations did not ignore that danger. In fact, they projected it forward as a warning. When researchers modeled future warming, they found that wet bulb temperatures would not commonly begin crossing the famous 35 degrees threshold until the planet had warmed by a very large amount. Roughly 7 degrees beyond the conditions of that time. Push warming still further, toward 11 or 12 degrees, and the regions considered unlivable outdoors would expand across land now occupied by an enormous share of humanity. Those figures are extreme, far beyond what is generally expected within this century, and for a time, that made the threat feel remote. The lethal boundary seemed to sit at 35, while the hottest wet bulb values observed on Earth appeared to peak near 31. That 4-degree gap sounded reassuring, almost like a cushion built into the climate system, but the comfort rested on one fragile assumption. The 35 degrees value was not a measurement taken from people in a laboratory. It was a theoretical estimate, built from physics and sensible ideas about how bodies regulate heat. No one had yet placed living volunteers inside a carefully controlled environment, adjusted heat and humidity with precision, and watched for the exact instant when the body could no longer maintain balance. In other words, 35 was a number drawn from calculation, not direct human observation. And when scientists eventually tested the question in real bodies rather than on paper, the answer shifted. The limit was not 35. It was noticeably lower, and that quiet change made the maps of future heat risk look much more troubling. This is the unsettling turn in the story. When the body itself became the instrument, the margin we thought we had began to shrink. Of course, the most direct experiment is impossible. No ethical scientist could put a person in a chamber, keep increasing the temperature and humidity, and wait for death to reveal the boundary. That would be morally unthinkable, and no ethics board on Earth would permit it. One scientist involved made the point plainly, saying in effect that you cannot place someone in a heat chamber and cook them. It would be unethical, and it would be murder. Yet there is a way to approach the edge without crossing it. A team at Pennsylvania State University, in work often known as PSU Heat, found a method. They did not need to carry volunteers to the point of death. They only needed to identify the moment the body stopped compensating, the transition from holding steady to losing control. That instant matters, because beyond it, survival becomes dependent on time and on whether the surroundings can be changed. The experiment began with young, healthy adult volunteers, people from their late teens into their 30 seconds. These were not the frailest members of society. They were among the most heat-resilient humans one could reasonably choose. Each volunteer swallowed a small telemetry capsule, allowing researchers to monitor core body temperature continuously from inside the body. Then the volunteers entered an environmental chamber, a sealed room where both heat and humidity could be adjusted with great care. Inside, they performed light activity, such as slow pedaling or gentle movement, enough to resemble the mild physical effort of ordinary life. Gradually, the researchers increased the environmental stress and watched what happened to the body's internal temperature. For much of the trial, the volunteers appeared to manage. As conditions grew hotter and more humid, their core temperature stayed nearly level. Sweating and other cooling mechanisms were still doing their work, allowing the body to defend its inner stability, while the outside world became less forgiving. Then, at a particular pairing of temperature and humidity, the pattern changed. The once stable line began to rise. More importantly, after that rise began, it did not simply correct itself. The body had passed from compensation into failure, from balancing its heat budget to accumulating heat faster than it could release it. Scientists describe this boundary as the limit of compensability, sometimes also called the limit of livability. It is the point beyond which core temperature climbs uncontrollably unless the person is moved into a cooler or otherwise safer environment. That distinction is subtle, but it is the hinge of the entire issue. The danger begins before collapse, at the moment the body can no longer keep up. So where did that threshold appear when measured in actual human beings? Not at 35 degrees wet bulb. In humid conditions, the critical wet bulb temperatures clustered around 30.5 to 31 degrees C, several degrees below the long-cited theoretical ceiling. Under hotter and drier conditions, the boundary was lower still. The neat, memorable figure of 35 had been too generous. It gave the body more resilience than real testing seemed to show. Even young, healthy volunteers, resting or doing only light activity, began to exceed their ability to shed heat earlier than the theory had suggested. Now return to that supposed buffer. Earth's most extreme wet bulb temperatures today reach roughly 31 degrees. The measured livability limit for a young, healthy person at rest or under light exertion sits close to 31 degrees, and in dry heat, it may be somewhat lower. The apparent 4-degree cushion between the worst conditions the planet can produce and the point of no return was therefore not a true safety margin. It was, at least in part, an artifact of using the wrong benchmark. In practical terms, the most severe humid heat already possible on Earth can press close to the survival limit for healthy adults. The threshold is not only waiting in a far-off world after 7 degrees of warming. Some places are already approaching it. That realization does not require exaggeration to feel serious. It simply asks us to replace a clean theoretical line with the messier limits of the human body. At this point, one more confusion has to be cleared away, because almost everyone stumbles over it at first. The newest and most detailed work on these uncompensable heat thresholds does not present danger as one universal number. Instead, it describes a range, extending from about 19 degrees C wet bulb up to roughly 32 degrees C wet bulb. Hearing the low end can sound absurd. A normal air temperature of 19 degrees C or 66 degrees F feels like a mild spring day, not a lethal environment. How could such a number belong in a discussion of human survival? The key is that wet bulb temperature is not the same as the reading on an ordinary thermometer. It already includes the effect of humidity, so it represents a very different kind of stress. A 19 degrees wet bulb does not mean the air feels like 19 degrees on a standard thermometer. In low humidity, a 19 degrees wet bulb can correspond to about 46 degrees on a regular thermometer, or roughly 115 degrees F. That is not gentle weather. It is an intensely hot, real-world day. This is why the language of wet bulb temperature can be deceptive at first glance. The number may look small, but the body experiences the combined burden hidden inside it. At a wet bulb reading of 19 degrees C, very humid air can mean an ordinary air temperature near 32 degrees C, or about 90 degrees F, only wrapped in heavy moisture. In other conditions, that same wet bulb value can belong to fierce, dry heat. Either way, 19 degrees wet bulb is not the gentle comfort the number might suggest. It can describe an environment that is already dangerous, and in some bodies, potentially lethal. The next question is the human one. Dangerous for whom? Why does one person reach the edge at a point another person can still endure? That question leads away from abstract weather charts and toward the people most exposed, most fragile, and most often lost when heat becomes extreme. To understand why, we need to slow down and look at what an unchecked rise in core temperature actually means. The phrase sounds neat and medical, but inside the body the process is urgent and chaotic. When heat is being made faster than it can be released, the core temperature begins to climb, and each small rise makes cooling harder. The heart speeds up, trying to send more blood toward the skin. Blood vessels widen, pressure may drop, and dizziness or confusion can begin. Once the core passes roughly 40 degrees C or 104 degrees F, the brain can start to fail in its basic work. A person may become disoriented, speak incoherently, collapse, or lose consciousness. At high temperatures, the proteins and cell membranes that keep the body functioning begin to break down. Organs can fail, and without fast cooling, the downward chain can become fatal. This is heat stroke, and it is an emergency where minutes can matter. Perhaps the most unsettling part is that confusion arrives early. The very ability needed to notice danger, make a plan, and escape may be among the first things heat steals. That is why researchers, looking for the true limit in living people, could not simply push subjects to collapse. They had to approach the boundary with great caution, watching for the first upward drift in core temperature and stopping before harm followed. In effect, they studied the threshold without forcing anyone through it. What they found at that threshold changed the older picture of human heat tolerance, and once the limit was clearer, along with the knowledge of who reaches it earliest and what happens inside the body, the next question became unavoidable. Where, on a warming map, does this doorway begin to open, and how many people are standing near it? Part 6 asks, who crosses that line first? The reason dangerous wet bulb thresholds stretch so widely, from 19 all the way to 32 degrees, is that the number is never only about the air. It is also about the body placed inside that air. A humid afternoon that a healthy 2-5-year-old might endure with discomfort could be catastrophic for a frail 8-5-year-old living nearby. The gap between those two outcomes is written into aging physiology. The PSU experiments described earlier used young, healthy adults because they represent the most heat-resistant version of the human body. The best-case scenario. Their limit, near 31 degrees, is not the average human boundary. It is closer to the upper edge for the strongest among us. Yet the people who die during heat waves are often not young, healthy adults. They are older, and in many quiet ways, an older body is less able to complete every stage of cooling. The thermoregulatory response becomes blunted. Overheating may be recognized later, and the response may come more slowly. Sweating is reduced. It begins later and occurs at a lower rate, meaning the body's evaporative cooling system starts with less power. The cardiovascular system may also struggle with the heavy demand cooling creates, because moving warm blood out toward the skin requires the heart to work hard. In a strained or aging heart, that added load can become too much. Older adults are also more likely to live with the chronic conditions that heat exploits. Cardiovascular disease, respiratory disease, diabetes, kidney problems. Each can make a hot day more hazardous, and many are treated with medications that can interfere with temperature regulation or hydration. Put together, these factors create a body that may cross the boundary of livability at a much lower wet bulb temperature than a younger person would. This is why the threshold has to be spoken of as a range rather than a single universal line. For a robust young adult, the danger point may sit near the upper end, around 31 or 32 degrees wet bulb. For a vulnerable older adult, it can drop toward that 19 degrees value that seemed harmless until the air temperature and humidity behind it became clear. A wet bulb level that leaves a teenager merely miserable may send an elderly person's core temperature into an uncontrolled rise. And age is not the only vulnerability. Infants and very young children regulate temperature poorly, with a high surface area to body ratio and no ability to take off clothing or get water for themselves. People doing heavy labor in heat, construction workers, farm workers, warehouse workers, are also producing intense internal heat through their muscles, on top of the heat imposed by the environment. That moves them toward the limit faster than a resting person. The same applies to athletes, soldiers, and anyone exerting themselves outdoors. Activity matters profoundly, because every watt of heat made by working muscles is another watt the body must shed. Seen this way, the threshold is not a single line drawn across humanity. It is a family of lines shaped by age, health, and exertion. The more vulnerable the body, the lower that personal line may fall. This is part of what makes heat such a quiet and cruel killer. It does not fall evenly across a population. It finds the old, the sick, the poor, the people working outside because they have no choice, and the people unable to cool their homes. It often kills indoors, alone, sometimes discovered only later. There is no dramatic wall of water, no splintered landscape, no obvious image for the evening news. Because of that silence, heat is often underestimated by the public and, in ways that matter, within the official record. When an elderly person with heart disease dies during a heat wave, the certificate may name the heart, not the heat that forced it beyond its limit. The real toll is therefore very likely higher than the official counts suggest. Across the United States, even using conservative official numbers, heat is the deadliest weather hazard. In a typical year, it kills more Americans than floods, tornadoes, hurricanes, or lightning. It is the #1 weather killer, working so quietly that many people would never suspect it. So the limit is no longer just a textbook abstraction. It has been measured in living bodies. It is real. And it sits lower than the old figure once implied. And, as so often happens in a climate emergency, the burden falls most heavily on those with the fewest ways to shield themselves. That brings us to the question this entire journey has been moving toward. If the physiological boundary is real, and if scientists can estimate where it lies, then where on earth do people begin to meet it? And when does that meeting become unavoidable? When researchers traced that danger across the map, the answer did not remain safely confined to remote tropical shorelines or distant places that feel easy to ignore. A significant part of the warning turned back toward the United States. But before that map can mean anything, we have to pause at one city where the line was not merely approached, it was crossed. In June of 2015, Karachi, Pakistan, offered one of the starkest real-world glimpses of humid heat, pushing beyond the limits of human endurance. This was not like Europe in 2003. And it was not like the Pacific Northwest in 2021, where dry heat played the central role. Karachi faced the more dangerous combination: extreme temperature joined to heavy moisture, the kind of air that makes the body's main cooling system begin to fail. The city lies beside the Arabian Sea, and that coastal setting matters because a warm ocean nearby can load the air with humidity. During that June event, temperatures in the region rose to around 45 degrees C, about 113 degrees F, while humid coastal air settled over a city of millions. In a dry desert setting, 45 degrees C can still be survivable for a healthy person who has water, shade, and time to rest. Add dense humidity, however, and the equation changes. Sweat can no longer evaporate efficiently, and without evaporation, the body loses the mechanism it depends on to shed heat. This is where the danger becomes intimate. The atmosphere is no longer just hot around you. It begins to interfere with the biology keeping you alive. Then the crisis began to compound, as heat disasters often do. Electricity demand surged because anyone with a fan or air conditioner tried to use it. The grid, already under stress, started breaking down, and rolling blackouts moved through the city. Once the power failed, many water pumps failed with it. In the same moment, people faced oppressive humid heat, little or no mechanical cooling, and reduced access to drinking water. Each problem sharpened the others. The timing made the disaster even more severe because the heat wave came during the holy month of Ramadan, when many residents were fasting and going without food and water during daylight hours. Hydration, one of the few defenses that might have helped people endure, was not available to everyone when they needed it most. Over roughly 10 days, the result became catastrophic. At least 1,200 people died. While some estimates of the wider regional toll are substantially higher, most deaths were linked to heat stroke and dehydration. Hospitals were pushed past their limits, morgues exceeded capacity and had to refuse bodies. Charitable groups that usually helped manage funerals could not keep up. By any humane measure, this was a disaster, and it did not require an unimaginable, once-in-10,000-year anomaly. It required a hot, humid, coastal megacity, a power system failing at precisely the wrong time, and people trapped inside conditions their bodies could not safely endure. That is why Karachi matters beyond Karachi. It turns an abstract threshold into a human scene. A city, a blackout, a shortage of water, and bodies losing the ability to cool themselves. The connection to the broader scientific picture is the part that should make us listen more carefully. After the 2015 Karachi event, scientists examined the observed heat and humidity and compared those conditions with measured limits of human livability. Their conclusion was alarming in its precision. For older adults, the heat wave crossed the uncompensable wet bulb threshold for about 8 to 10% of its duration. That number can sound small until its meaning settles in. For roughly 1/10 of the event, the air reached a point where, by the physiological standard, it was genuinely unsurvivable for an older person, even with shade, water, and rest. The boundary discussed so often, as if it belonged to some distant future, had already appeared in a real city, among real people, in 2015. It did not engulf the whole event from beginning to end, and it did not affect everybody in the same way. But for the most vulnerable, during that meaningful slice of time, the line was crossed. The lesson is quiet, but severe. A threshold does not need to last forever to leave a city overwhelmed. Now, the warming trend tightens the story. Karachi, 2015, occurred in something close to today's climate. The deepest concern is not only what happened then, but what a comparable event becomes as global temperatures rise. Scientists modeled that future, and the pattern grows darker in a very specific way. At 2 degrees C of global warming, a level we will return to because of how soon it may be reached, a similar heat wave would no longer exceed the uncompensable threshold only for older adults. It would begin to cross that boundary for younger adults as well. In other words, the barrier that in 2015 was mainly a danger for the frail would begin pressing against people with stronger heat tolerance, the young, the fit, and the otherwise healthy. If warming reaches 4 degrees C, the upper range of what remains possible if emissions continue unchecked, the same kind of Karachi-style event would exceed the uncompensable threshold for older adults for about 90% of its duration, not 8 to 10%. About 90%, a heat wave that is now briefly unsurvivable for vulnerable people would, in a 4 degrees C world, become almost entirely unsurvivable for them from beginning to end. That change is not just a larger number, it suggests a different kind of event, one in which recovery time nearly disappears. Karachi, then, should not be treated as a tragedy from somewhere far away and fundamentally separate from everyone else. It is better understood as a preview. One of the clearest early images of a danger moving outward into a warming world. The variables that shape who faces their own version, and how often, are painfully simple. How much more the planet warms, and how prepared communities are when the humid heat arrives. From here, the story turns to the map, because researchers have taken these measured limits of human livability and placed them over projections of a warming planet. The result shows where, and roughly when, these dangerous conditions begin to take hold. For anyone in the United States, the direction of that map is not something to dismiss. Still, it is tempting to misunderstand the Karachi number. One might look at 8 to 10% and imagine that if the air was only briefly beyond the limit, most people were probably safe most of the time. The deaths tell us otherwise. A city's morgues do not require lethal air every minute of every day. It may be enough for the atmosphere to pass the threshold for repeated stretches of hours, especially when those hours land on people who are elderly, ill, isolated from cooling, or exhausted by nights that bring no real relief. A few percent of a 10-day ordeal still amounts to many hours of truly unsurvivable air, returning again and again to bodies that have not recovered from the previous assault. At least 1,200 people died in a heat wave that, by the strict physiological measure, crossed the ultimate boundary for only a fraction of its duration. That is the disturbing scale of the risk. A small window of uncompensable heat can be enough when it opens over vulnerable people. Carry that same arithmetic into a warmer future, and the implication becomes profoundly unsettling. Karachi happened roughly in the climate we already know. Place that same heat event inside a world warmed by 2 degrees C, and its danger changes character. The deadliest hours would no longer belong mainly to the elderly or medically fragile. They would begin to press beyond what even healthy young adults can compensate for. In other words, the circle of direct physiological risk expands from a narrow, vulnerable group toward the wider public. If the planet reached 4 degrees C, the transformation would be far more severe. That heat wave would remain beyond the survival threshold for older adults for something like 90% of its duration. What had been briefly fatal for some could become nearly continuous danger for many. The weather itself does not need to become stranger, rarer, or more cinematic. Put the same pattern of heat onto a warmer Earth, and it spends a larger share of its life past the boundary the body can endure. Karachi, then, is not something to close away as an isolated tragedy. It may be better understood as an early image from a story still unfolding. Part 8. The Map of 2 Degrees. When scientists apply measured limits of human livability to projections of a warming planet, the result can look deceptively familiar at first glance. Continents, seas, coastlines, and patches of color. Yet those colors are not simply forecasts of discomfort or summer extremes. They mark places where, at a given level of global warming, the atmosphere is expected to move beyond what a human body can survive. These are not ordinary weather maps. They are maps of the crossing point. Begin with 2 degrees C above pre-industrial levels. That number deserves care, because it is the pivot on which this whole discussion turns. A 2 degrees world is not some remote, end-of-century idea reserved for people we will never meet. Earth has already warmed by well over 1 degree, and on the present path, 2 degrees could arrive in as little as 2 decades. That places it inside the lives now being lived. within the career span of a young adult, and within the retirement years of someone middle-aged today. At that mark, the modeling suggests that about 35% of Earth's land area would periodically face wet bulb conditions that are uncompensable for older adults. More than 1/3 of the planet's land could, at times, produce outdoor heat an elderly person cannot survive. But the number alone softens the shock. Because land is not the same thing as human exposure. Empty mountains, deserts, and ice sheets are all counted in land area. The deeper question is whether the shaded zones overlap with the places where people actually live, and they do. They fall across some of the most densely populated regions on Earth. At 2 degrees, the danger zone includes most of India, a country moving toward 1.5 billion people. It extends over much of the populated east of China. It spreads across vast areas of South and Southeast Asia, through a humid, coastal, already hot belt that contains the greatest concentration of human beings on the planet. This is not a warning about a faraway wilderness or an uninhabited edge of the map. It is about river valleys, coastal plains, and megacities, the places where billions have gathered because they were, for so long, places where life could flourish. And then the map reaches a region that should make an American audience pause. At 2 degrees, the danger zone also covers much of the eastern United States, not only Phoenix, not only Death Valley. The east, humid, crowded, surrounded, and shaped by water, from the Gulf Coast through the Mississippi Valley, into the Midwest, and across the Southeast. These are not the landscapes many people imagine when they picture apocalyptic heat. They are places of green lawns, afternoon thunderstorms, and summers associated with swimming pools more than survival thresholds. Yet those are the American regions, the modeling shades. That raises a quiet but urgent question. Why would the eastern United States appear on a map of human heat limits? We will turn to that next. Now move the planet from 2 degrees C to 4 degrees C above pre-industrial levels, the higher end of what becomes possible if emissions remain high, or if the climate system responds more strongly than central estimates assume. The image shifts from disturbing to almost unfamiliar. At 4 degrees, more than 60% of Earth's land mass could experience these dangerous wet bulb temperatures. Much of the inhabited world would periodically produce heat beyond the human limit. A few degrees, in this context, are not a small adjustment on a thermometer. They separate a grave, costly, painful challenge from a planet in which large regions become seasonally hostile to the species that built cities there. To make the 2 degrees world feel less abstract, return to a place already in the story, Paris in 2003. That dry heat dome killed thousands, and at the time it landed as an event so far outside the historical pattern that it felt like a once-in-a-century disaster. Scientists found that with 2 degrees of warming, Paris could see deadly heat waves like the 2003 event, not once in a century, but once every few years. A catastrophe once treated as generational becomes something a city must expect again and again, almost as it prepares for winter. And it matters that 2003 was dry heat. It never even crossed the wet bulb line. So the merely catastrophic begins to repeat, while above it a harsher category, the genuinely unsurvivable, moves closer. That is the outline taking shape. A real physiological boundary, lower than many assumed, hardest first on the vulnerable, carried by a warming atmosphere toward the most crowded land on Earth, including large parts of the United States, within the lifetimes of people hearing this now. So we go to that map. We ask why the eastern United States, of all places, belongs on it, and what a wet bulb event might look like if it arrived in an American city. To understand the human scale of the 2 degrees map, set aside percentages of land for a moment and think in people. The danger zone, at 2 degrees, does not settle mainly over empty portions of the globe. It falls on the river valleys and coastal plains where humanity concentrated itself because those places were fertile, useful, and habitable. India alone is moving toward roughly 1.5 billion people, the largest population on Earth, with much of that population in the hot, humid, low-lying north and east that the maps mark. The populated eastern half of China adds hundreds of millions more. Include the rest of South and Southeast Asia, along with much of the Middle East, and the picture is no longer an abstract climate graphic. It becomes a count of billions of people living in regions projected to periodically enter conditions that an older body cannot survive outdoors. These are not scattered frontier settlements. They are among the most densely inhabited places that have ever existed. The most unsettling part is the clock. A rise of 2 degrees is not simply a marker placed far away at the year 2100. Earth has already warmed by more than 1 degree above the pre-industrial baseline, and if the present course continues, that 2 degrees threshold could be reached in about 2 decades. A child born now might still be in school. Someone in their 40s today could encounter it before a typical retirement age. So this is not a burden being passed to an unnamed generation in some distant century. It is moving into the span of lives already being lived, including the lives of people listening now and of their children. That is part of what makes the threat so quietly dangerous. It does not burst into attention like a single storm crossing a coastline. It gathers slowly, year after year, until what once looked like a projection begins to resemble the world outside the window. In that sense, the timeline may be the most sobering map of all. Part 9. Why it is coming for the American East. If someone were asked to name the region of the United States most vulnerable to heat that humans cannot safely survive, the common answer would almost certainly be the Southwest. Phoenix, Las Vegas, the desert cities, where temperatures can regularly climb beyond 115 degrees F. Those places do experience severe heat, and people do die there. Yet the wet bulb maps point toward a less obvious danger. Deserts are fierce, but they are also dry. In dry air, sweat can still evaporate, and evaporation is the body's cooling system. The desert may strain that system brutally, but much of the time, it does not fully shut it down. The place where that inner radiator begins to fail is not necessarily the hottest desert. It is the humid, water-rich eastern half of the country, where heat arrives wrapped in moisture. That distinction matters, because the question is not only how high the thermometer rises, but whether the human body can still shed heat at all. The explanation begins with geography. The eastern United States lies beside 2 vast sources of warm water. To the south sits the Gulf of Mexico, a basin of very warm seawater that has been at or near record temperatures in recent years. To the east is the Atlantic, with its own growing areas of marine heat. Together, these waters act like immense moisture engines, feeding water vapor into the atmosphere. Prevailing winds can then move that damp air across the Gulf Coast, up through the Mississippi Valley, across the southeast, and onward into the Midwest and the Ohio Valley. It is the same moisture behind the famously muggy summers of the American South, the kind of morning air that can leave a shirt damp before someone has even reached the car. For now, people may laugh about that heaviness, but in a warmer climate, that familiar humidity becomes one of the exact ingredients that can push heat toward wet bulb danger. The physics makes the risk sharper. As air warms, it can hold more water vapor, roughly 7% more moisture, for every single degree of warming. In a region such as the American Southeast, where moisture is already supplied by the Gulf, rising temperature does not merely make the air hotter, it also increases the air's capacity to carry water. And when a warm ocean is close enough to provide that water, humidity can rise alongside the heat. The 2 parts of the hazard then reinforce each other. Hotter air and wetter air, moving together toward higher wet bulb temperatures. The South does not need to import this danger from somewhere else. It already has the heat source. It already has the moisture source. Warming may turn both controls upward at the same time. In a calm forecast, that might sound technical. In a human body, it becomes the difference between cooling and not cooling. Now imagine what a true wet bulb event could look like in an American city, because this is no longer a scenario that belongs only to Karachi. Picture a large metropolitan region along the Gulf Coast or in the lower Mississippi Valley during the depth of a future summer. A heat dome settles overhead, as one did over Europe and the Northwest. But this time, it rests above a landscape saturated with Gulf moisture. During the day, the heat index climbs into a range with no real regional precedent. Even then, the most dangerous moment may not be the afternoon high. It may be what happens after sunset, when the normal relief fails to arrive. Usually, night acts as the release valve after a hot day, allowing temperatures to fall and bodies to recover. In a humid heat event, however, the water vapor in the air holds onto the day's warmth like insulation. The overnight low does not fall enough for people to reset. One day's heat becomes the starting point for the next. And bodies accumulate stress without a real pause. In many events like this, that unbroken nighttime flaw can become the quiet killer. Then come the failure modes, already visible from past disasters, the same kinds of breakdowns that helped turn Karachi from a heat wave into a mass casualty event. Across a city, electricity demand surges as millions of air conditioners run continuously. The grid itself deserves a closer look, but for a moment, hold the image of that load pressing against the system. Then add the compound disaster that specialists in this field genuinely worry about: a hurricane. Powered by those same warm Gulf waters, comes ashore first and cuts electricity across a broad region. In the days that follow, while repair crews are still working and the grid remains down, a humid heat wave settles over that same place. Suddenly, people have no air conditioning, no refrigeration, and in some areas no functioning water systems, all while extreme humid heat persists for days. That sequence, a heat wave arriving on top of a storm-broken grid, is among the most dangerous compound scenarios we face. And as hurricanes and heat waves intensify in a warming climate, the chance of these hazards arriving back-to-back continues to rise. The fear is not just one event, but the way one failure can open the door for the next. This is why the eastern United States appears on the danger map. Not because it will become the hottest place on Earth. It will not. Its vulnerability comes from the combination: heat, moisture, a very large and often underprepared population, an aging grid, and hurricane risk that can remove the one protection many people depend on. The threat is neither abstract nor foreign. It is being assembled piece by piece across a region where tens of millions live, and where many may still think of their familiar muggy summer as merely uncomfortable rather than as an early version of something far more dangerous. That raises a difficult question. What happens when the ordinary background feeling of a place becomes a warning signal? The answer may depend on whether people recognize the pattern before it reaches its most dangerous form. And that single protection so many people trust the air conditioner needs its own hard examination. It can be a brilliant machine, but it is also flawed and, in a quiet way, self-defeating. Return one more time to that future American heat event and set it beside the threshold we have been tracing. A heat dome stalls over a Gulf Coast metropolitan area, drenched in ocean moisture. The wet bulb temperature, the measurement that tells us whether a human body can cool itself, climbs day after day toward the limit revealed in chamber experiments. For the young and healthy, the air moves close to the edge of what the body can compensate for. In that narrow margin, survival may appear to depend on a switch, a compressor, and a power grid still holding together. For an older person trapped in an apartment where the cooling no longer works, the threshold may already have been crossed. The night, once the hours when the body could recover, offers no real mercy when humidity keeps the day's heat suspended in the dark. After several nights like that, a body that cannot shed heat does not simply remain uncomfortable, it begins to lose ground. This is not some distant calamity placed safely elsewhere on the map. It is a believable American summer in the direction those maps suggest, and the difference between survival and a Karachi-scale tragedy could come down to one simple question. Can the air around vulnerable people be cooled? That is an enormous burden to place on one class of machine. It means the weaknesses of that machine are not minor engineering details. They may decide whether our last line of protection holds, or whether it breaks exactly when it is needed most. So we need to examine those weaknesses plainly, beginning with a misconception so basic that it hides in plain sight: what an air conditioner actually does. In a story about heat, that misunderstanding matters, because it may be the first fissure in the wall many people assume is solid. Part 10. The only defense left. To see why cooling becomes so decisive, we have to return to the boundary itself, because everything depends on one harsh physical reality. When the air around a person moves beyond the limit of livability, when the wet bulb temperature rises higher than the body can compensate for, nearly all the familiar advice about staying safe begins to fail. That is the difficult idea, because it contradicts what experience has taught most of us. The scientists are not exaggerating when they describe it. They are speaking in literal terms. A breeze no longer saves you. Shade no longer solves the problem. Drinking water, by itself, cannot restore the body's cooling system. Once the threshold is passed, those measures lose the power we normally expect from them. The reason is the same physics that has been guiding this entire discussion. Moving air can cool skin only if sweat is able to evaporate. Beyond the line, the air is already too loaded with moisture, so the breeze merely carries hot, wet air across the body without giving it a way out. Shade can reduce the radiant heat from direct sunlight, but past this point, the central threat is not sunlight falling on the skin. It is the heat and moisture in the air itself, and that air can be just as dangerous undercover as it is in the open. Water feels like the obvious answer because it helps the body keep sweating. Yet sweat cools only when it can turn to vapor. If the surrounding air will not accept that moisture, the cooling process stalls. A person could drink endlessly or pour water over their head, and still the core temperature would keep rising. Because the shortage is not sweat. The blockage is the atmosphere's refusal to take it away. That is the quiet terror of the wet bulb limit. It turns ordinary survival instincts into tools that no longer reach the mechanism of danger. When the body has no remaining way to unload heat on its own, the choices narrow to one. The air must be changed. The space around the person has to be physically cooled, or the moisture has to be removed. So evaporation can begin again, and the body's internal radiator can function. In the modern world, the machine that can do this when asked is the air conditioner. That is why, in this context, scientists treat air conditioning not as a pleasant convenience or a status symbol, but as the major adaptation and protection measure available. It can become the barrier between vulnerable people and air that the body cannot survive. When a humid heat wave settles over a city and the wet bulb temperature approaches the limit, the dividing line becomes painfully clear. People inside cooled buildings have a chance, while those without cooling are far more likely to appear in hospitals and morgues. In heat disaster after heat disaster, the deciding factor has not been toughness, discipline, or how much water someone managed to drink. It has been whether they had a working and affordable way to cool the air around them. At first, that might sound almost comforting. We possess the machine. It was invented a century ago. Hundreds of millions of homes already have it. So it is tempting to think the matter is basically solved, or at least that the solution is obvious. Build more air conditioners, turn them on when the heat arrives, and extend that protection to everyone who needs it. If air conditioning is the answer, then perhaps the answer is already sitting in our windows, on our roofs, and beside our homes. But this is where the story changes shape and where the reassuring conclusion begins to crack. Air conditioning truly saves lives, and the response to deadly heat must be broader access to cooling, not less of it. Yet the machine we are leaning on carries weaknesses so serious that, if they are left unaddressed, our strongest defense could also intensify the crisis it is meant to resist. Cooling is expensive, which means it is distributed unevenly, often in precisely the places where inequality makes danger worse. It relies on an electrical grid that was not built for the scale of demand a hotter future could impose. And at the dark center of the problem sits a troubling loop. In much of the world, the electricity used to power cooling is produced in ways that make the planet warmer. To understand that trap, we need to look closely at the machine itself, because many people picture it incorrectly. The truth is simple, but it changes the meaning of every humming unit in a hot city. Part 11. The machine that only moves heat. Here is the part many people miss about the air conditioner cooling a room right now. It does not make heat disappear. It cannot do that. Nothing can. An air conditioner is not a device that erases heat from existence. It is a device that transfers heat from one place to another. Once that becomes clear, the first major problem comes into focus. And a city filled with cooling machines begins to look less like a complete escape and more like a system with a hidden cost. The basic operation is straightforward. The air conditioner takes heat from the air inside a home and pushes that heat outside. Indoors, a cold coil draws warmth out of the room, and the room becomes cooler, but the warmth has not vanished. A circulating refrigerant carries it to the unit on the roof or next to the building, where it is released into the outdoor air. That is why the air coming off the back of an air conditioner feels hot. The machine is not eliminating the heat in the home. It is moving that heat outdoors, while also adding the energy the machine consumes as extra heat in the process. For a single house, this may seem small enough to ignore. Scale it up though, and the picture changes. On a punishing afternoon, hundreds of thousands, even millions of air conditioners across a metropolitan area can be running at the same time. Each one is extracting warmth from an interior space and ejecting it into the city air outside. The heat that has been displaced, together with the waste heat from the machines themselves, flows into streets, courtyards, alleys, and the air trapped between buildings. The room becomes safer, but the surrounding city may become more burdened, and that raises the uncomfortable question at the heart of this defense. What happens when the tool that protects individual bodies also adds heat to the shared environment around them? When we cool the rooms around us, we do not make heat disappear. We move it. In a city, that displaced warmth is pushed into streets, courtyards, alleys, and the air between buildings, so the comfort created indoors can measurably add to the heat outdoors. This matters because the city is already shaped like a thermal trap, and during heat waves that design can become dangerous. The urban heat island effect begins with ordinary materials: dark asphalt, flat roofs, concrete, brick. They take in sunlight through the day, hold it, and release it slowly after sunset, much as the stone buildings of Paris held heat during 2003. With fewer plants to cool the air by releasing water vapor, and with dense walls of buildings interrupting the movement of wind, the center of a city can remain several degrees warmer than the surrounding countryside. The difference is often most important at night, just when relief should arrive. That is when heat deaths tend to cluster, because bodies that cannot cool down after dark are steadily worn down. Into this already burdened environment, millions of air conditioners add the heat they have pulled from indoor spaces, pushing the shared outdoor air slightly higher at the very moment when each degree can matter. There is a harsh symmetry in this machine. As more residents turn on air conditioning to endure the heat, more waste heat is expelled into the same urban air used by everyone outside. People without shelter, people waiting at a bus stop, people working on construction sites, and people who have no air conditioner to use. The comfort of those protected indoors can, in a small but real way, deepen the strain on those left exposed. Air conditioning is not the main cause of the urban heat island, but it becomes a clear symbol of a larger pattern running through this story. A technology that shields some people may quietly make conditions harder for others. That brings us to the second great fault line. The question of who is allowed to be cool at all. If access to air conditioning can decide whether someone survives a wet bulb event, then the ability to buy the machine, install it, and pay to operate it becomes more than a household expense. It becomes a matter of life and death, and that is one of the most uncomfortable truths in the subject. The nighttime side of the urban heat island deserves a closer look, because this is where the city does its damage most silently. In daylight, the temperature gap between a city and the rural land beyond it may seem limited, partly hidden by sunlight falling on both places. After sunset, the contrast can grow. The countryside releases heat into the night sky and begins to cool, while the city struggles to let go. Asphalt, concrete, and brick, having absorbed energy all day, give it back slowly, hour after hour. The relocated warmth from countless air conditioners adds to the burden. And the closeness of buildings can prevent breezes from carrying heat away. In the deep night, the urban core may still sit many degrees above its surroundings, exactly when the human body most needs a cooler environment to recover. The great heat dome disasters have already shown how deadly the loss of nighttime cooling can be. In effect, the city builds that failure into its materials and layout, then concentrates it most severely in neighborhoods with little shade and few resources to resist it. The picture that emerges is not just of heat as a physical hazard, but of heat as an unequal one. It sorts risk by income, by geography, and by the accident of which neighborhood a person can afford. On the same night, under the same larger weather event, one part of a city may experience discomfort, while another, only a few miles away, faces mortal danger. This inequality is not a secondary issue beside the survival threshold we have been following. It is part of the threshold itself. The limit of livability is not crossed by all people at the same time. It is reached first, and most often, by those already placed closest to exposure. That is why the advice to simply turn on the air conditioning can sound so empty. A real defense must reach people who have no machine waiting on the wall, no safe room to retreat into, and no easy way to buy relief when the air itself becomes dangerous. Part 12. Who gets to be cool? If survival during a wet bulb event depends on cooling, then the question has to be asked plainly: who has access and who does not? Air conditioning is distributed unevenly across the planet, and also unevenly within individual cities. The pattern is painfully familiar. Those most likely to lack cooling are often the same people most exposed to deadly heat in the first place. Begin with cost, because the barrier has two layers. First comes the price of buying and installing equipment, which can be far beyond reach for a low-income household. Then comes the continuing cost of electricity, and that can become the more persistent trap. Cooling uses a great deal of energy. Running an air conditioner through a long, severe summer can push an electricity bill to levels that feel punishing. As the climate warms and hot seasons become longer and more intense, those bills are expected to rise. Even people who own an air conditioner may face an impossible calculation during a heat wave. Run the machine enough to stay safe, or keep the bill low enough to pay. Many end up rationing cooling. They set the thermostat higher than safety would suggest, or shut the unit off when they leave, even if the home will heat like an oven while they are gone. Each year, some people ration that protection until the choice becomes a medical emergency. Widen the view from a single household to the globe, and the injustice becomes sharper. Many of the regions most exposed to extreme humid heat, including parts of South Asia, the Middle East, and the developing tropical world that lie within the danger zones on those 2-degree maps, are also places where large portions of the population have little or no access to air conditioning. The people living closest to the threshold are often those least able to purchase safety. It is a severe alignment, The heat arrives first and hardest in many places, least prepared to defend against it, while the defense itself remains too expensive for many of the people who need it most. The same pattern appears even in wealthy countries, even inside American cities. Study after study has found that the hottest neighborhoods in a city, the ones with the most pavement, the fewest trees, and the strongest urban heat island effect, tend to be lower-income neighborhoods. In many cities, the people facing the fiercest heat are often those living in neighborhoods marked by decades of disinvestment. Just a few streets away, wealthier districts may feel like a different climate altogether. Older trees cast shade, parks and private yards soften the air, and central air conditioning can run without the bill becoming a crisis. On the same dangerous afternoon, inside the same urban boundary, two groups can therefore inhabit two very different thermal realities. For one, the heat may be miserable but survivable. For the other, it can become a direct threat. That divide is not random. It reflects income, planning choices, and the long history of how the city took shape. This is why public health experts warn that extreme heat protection cannot be reduced to telling people to switch on air conditioning. That instruction quietly assumes access to the machine, the wiring, and the money to pay for electricity conditions that millions of vulnerable people do not share. A serious response has to include cooling centers, meaning public air-conditioned places where anyone can take shelter from dangerous temperatures. It also requires help for low-income households, not only to obtain cooling equipment, but to keep it running when the bill arrives. And it means looking first toward the elderly, the isolated, the sick, and the people least likely or least able to call for assistance. Air conditioning can be a shield. But if that shield is available mainly to those who are already comfortable, it cannot solve a hazard that falls hardest on the poor. Yet even if we imagine that barrier disappearing, even if every household could buy an air conditioner and afford the electricity, the danger would not simply fade away. A second obstacle remains, less social and more physical. It sits behind the question of cost, and it may be even harder to confront: the electrical system itself. If everyone turns on cooling at once, all those machines place their weight on the same network, and the power grid was not designed for the hotter world now approaching. This is where the problem widens from individual homes to the hidden infrastructure beneath modern life, raising a quiet but urgent question. What happens when the very system meant to deliver safety becomes fragile at the exact moment safety is needed most? Part 13. The grid was never built for this. Each year, there is one day that grid operators can usually sense before it arrives. It is, almost always, the hottest day, because that is when millions of people respond in the same way, at nearly the same hour, by reaching for the same switch. Electricity demand then rises toward the outer limit of what the system can provide. An air conditioner, in an ordinary home, is among the most electricity-hungry appliances. During a punishing afternoon, nearly every unit across a region may be running, and many are working at full strength for hours. Engineers call that demand the load, and in these conditions, the load becomes immense. It tends to crest in the late afternoon and early evening, when temperatures are still severe and people are returning home. Grids do include extra capacity for moments like this, but that reserve is not endless. It was planned from older expectations. How hot days used to be, how many cooling units were once running, and how long the peaks were expected to last. As the climate warms, those peaks grow taller, stretch longer, and press closer to the system's ceiling. When demand nears or passes what the grid can supply, failure begins to move from possibility to threat. Equipment is pushed too hard. Transformers, which lower voltage so electricity can be delivered into neighborhoods, heat up and may stop working. Extreme heat makes that failure more likely, because those devices also depend on the surrounding air to shed heat in a way that faintly echoes the vulnerability of the human body. Power lines can sag in high temperatures and carry less electricity. To avoid a wider, uncontrolled collapse, Grid operators may sometimes order planned outages, cutting power to certain areas to protect the whole system, as happened in Iraq. The cruel timing is the heart of the danger. Cooling demand is greatest on the hottest day, and that same day is when the grid is under the most strain. So the electricity is most likely to disappear exactly when cooling may decide whether people live or die. One expert who studies this risk has described the logic in stark terms. If air conditioning is treated as the only protection, then any failure of the power system, whether from overload or from other damage, instantly places everyone dependent on that cooling in danger. The protection does not slowly weaken. It can vanish in a single moment across many homes at once during the worst heat. 1 minute, a vulnerable neighborhood may be surviving because its air conditioners are running. The next, if the grid trips, those units fall silent together, and time begins to matter for everyone inside. This is not a distant scenario. Grids across the United States and around the world are aging, and many are already stretched by normal summer demand. Meanwhile, new electricity needs are rising from other directions as well. Electrified cars and heating, and the rapid expansion of power-hungry data centers, all drawing from the same supply. Year by year, the gap between what people require and what the grid can reliably deliver can become narrower. We are asking an old and heavily burdened system to carry an increasing surge precisely when heat makes it most vulnerable. The more we depend on air conditioning as the main shield against lethal temperatures, the more we bind our safety to a network whose collapse on the wrong day could be disastrous. That leads to the particular scenario that specialists in this field often fear most. It is not merely a heat wave, it is a heat wave arriving after something has already damaged or weakened the grid. The reason electricity sits at the center of this fragility is that, unlike many essentials, it cannot be easily stored at large scale. It must be produced almost at the same instant it is consumed, so supply has to rise and fall with demand minute by minute throughout the day. In mild weather, that balancing act is manageable. On the hottest day of an intense summer, with cooling demand climbing toward a record, operators are balancing on a narrow edge, calling on every available source of generation to keep pace with a load that keeps rising. There is little room for error. And in a final unsettling symmetry, the same extreme heat that drives demand upward can also weaken the system's ability to supply power. When temperatures climb, the electrical system is stressed from several directions at once. Power plants can operate less efficiently in extreme heat, transmission lines may carry less electricity, and machines that rely on the surrounding air to shed heat begin to struggle, much as the human body does. At the very hour when people need the most cooling, the grid's ability to provide it can be at its most fragile. It is a dangerous alignment, almost as if the system has been arranged to falter at the least forgiving moment. And as more of daily life becomes electric, that narrow balance becomes even more delicate. Electric vehicles, electric heating and cooking, and vast, power-hungry data centers are all being added to the same shared supply. Each one may be sensible on its own. Together, placed on top of an older grid that already strains through hot afternoons, they reduce the cushion between demand and delivery, precisely when that cushion matters most. In a wet bulb event, a power failure would not merely be disruptive. It could mean the sudden disappearance of the only protection available to an entire region. That is why experts who study these risks often point not to heat alone, but to what happens when heat arrives after something else has already broken the system. Part 14. When the lights go out at the worst moment. If you ask researchers of extreme heat what situation worries them most, many do not begin with a single record-breaking temperature. Instead, they describe a chain reaction, one disaster followed closely by another, so that the shield people depend on is removed just as it is needed. These are known as compound hazards, and they are becoming a deeper concern as different forms of extreme weather intensify together. The picture is simple enough to understand. which is what makes it so unsettling. Imagine a major hurricane, strengthened by ocean water, made warmer by climate change, moving inland along a heavily populated coastline, somewhere near the Gulf or the southeastern United States. The storm behaves as hurricanes do. It brings down power lines, floods, substations, and leaves a broad area without electricity, perhaps for days, perhaps for weeks, as major storms have repeatedly done. Then the obvious violence passes. The winds weaken. The rain ends. Floodwater starts to drain away. Public attention begins to drift because the spectacular phase seems finished. But then heat settles over the same damaged landscape. The same season and warm ocean conditions that helped create the hurricane can also be followed, only days later, by a humid heat wave in that very region. Now, however, the power is gone. Air conditioners are silent. Refrigerators no longer preserve food or medicine. In some places, water systems dependent on electric pumps have stopped functioning as well. Hospitals may be relying on backup generators, if they are functioning at all, while already coping with the storm's injuries. Into this weakened setting, the wet bulb temperature begins to rise. A whole population has lost, all at once and across a wide region, the modern protections that normally stand between people and lethal heat. There may be nowhere practical to evacuate to, and no reliable way to cool the body, because the protective network failed with the storm. This is the failure pattern that specialists fear. The reason is not mystery, it is probability. Each part of the sequence is becoming easier to imagine. Hurricanes draw energy from warming seas. Heat waves are becoming more common and more severe. And the interval after a storm, when a battered region may still be without electricity, is exactly when heat can become most deadly. One researcher has described these overlapping hazards, such as a heat wave following a hurricane, as an increasing concern as warming approaches the human limits we have been tracing. The danger is not that every separate event has never happened before. It is that the chances of them arriving in layers keep rising. When they do, the harm is not simply added together, it can be multiplied. Quietly, this kind of compound disaster reveals something larger. It shows how brittle our present strategy may be. In practice, we have placed survival during extreme heat on the uninterrupted operation of a complex electrical machine. While current flows, the plan can work, and people can remain alive indoors. But there is very little fallback in the design. Once power fails, whether because of a storm, an overloaded grid, or some other shock, the situation returns to something stark: the unprotected human body facing the physics of hot, humid air. On the wrong side of that threshold, the body cannot win. We have not truly moved beyond the boundary of livability. We have concealed it behind machinery, and that machinery is only as dependable as the grid feeding it. Yet, there is another level beneath this problem, and it may be the most troubling one, because it is not only about price, access, or reliability. It concerns the source of the energy behind our protection. At the moment, the way much of the world powers its defense against heat is also helping to intensify the heat itself. The remedy is strengthening the illness. To see that trap clearly, we have to trace the electricity back to its origin. Part 15. The trap we have built. At the center of the story sits a paradox that turns a hard problem into something more like a snare. The air conditioner has become the main defense against dangerous heat, but operating air conditioners at vast scale requires enormous amounts of electricity. Across much of the world, most electricity is still generated by burning fossil fuels, and that process releases greenhouse gases that warm the planet. So when people cool themselves on a fossil-fueled grid, they can add more of the very emissions that are making future heat worse. The protection reinforces the danger. In a very real sense, we may be cooling our rooms while helping to heat the world outside them. The scale is easy to underestimate, so the numbers matter. Air conditioning, along with the wider category of space cooling, already produces roughly 3% of global greenhouse gas emissions. That is about 3% of the entire planet's emissions devoted to keeping indoor spaces cool. At first glance, the figure may not sound overwhelming, but it belongs to a single broad category centered on one kind of need, and that need is expanding rapidly. As the planet grows hotter, and as billions of people in quickly warming developing countries reach the income level where a cooling unit becomes affordable, demand is expected to climb sharply. The question this leaves hanging in the warm air is unsettling. How do we protect people from deadly heat without deepening the conditions that make that protection ever more necessary? According to the International Energy Agency, the global stock of air conditioning units is expected to come close to tripling by 2050. That one projection carries a quiet weight, nearly 3 times as many machines, each one asking for electricity, and, if present trends continue, most of that electricity still coming from grids tied heavily to fossil fuels. The pattern is not difficult to trace, but it is deeply unsettling. As the planet grows hotter, more people turn to air conditioning, and those who already have it run it longer and harder simply to endure the heat. That extra cooling raises demand for power. When that power is produced by burning fossil fuels, more greenhouse gases enter the atmosphere. Those gases then intensify the warming, which increases the need for still more cooling. The circle tightens with every pass. In calm terms, it is a feedback loop. In human terms, it means that one of our strongest defenses against heat can, if powered the wrong way, help create more of the danger it is meant to protect us from. Researchers studying this problem have asked the central question plainly. If humanity tries to solve the heat crisis mainly by installing more air conditioning, how much additional pollution would that create? And how much would that pollution add to future warming? The answer appears to be large enough to matter. It suggests that cooling, when linked to fossil fuel electricity, can become one more gear in the warming machine. This is the trap. Air conditioning cannot simply be rejected, because in dangerous heat it is not a luxury. It can be the line between survival and death. As temperatures rise, the world will need more cooling, not less. Asking people in a wet bulb danger zone to reduce cooling would be asking them to accept a life-threatening risk. So there is no safe retreat into the past. Yet continuing on the present path, building an ever larger fleet of cooling machines, while powering them through fossil-fueled grids, would push the very warming that makes those machines more necessary. We are left facing a difficult symmetry, a protection we cannot abandon, attached to an energy system that worsens the crisis it is defending us from. Still, the picture should not be mistaken for hopeless. The way out is not simple, and it will not happen by itself, but it is real, and it rests on physics and engineering already within reach. The loop closes because of one particular connection in the chain. Fossil fuels burn to generate electricity. Remove that connection, and the trap begins to open. This is why a subject as severe as the edge of human livability, the maps of heat people cannot survive, the frailty of power grids, and the danger of overlapping disasters points with unexpected clarity toward one central answer. The answer is not mainly about heat. It is about the source of power. Part 16. How the trap springs open. The trap depends on only one link. Air conditioning itself is not what heats the planet. The problem is the combustion of fossil fuels used to produce the electricity that operates it. The movement of heat from indoors to outdoors, the relief inside a cooled room, the lives protected during a heat wave, none of those actions releases greenhouse gases on its own. The emissions come from the way the electricity is made. That distinction matters, because it changes the solution. In a warming world, the goal cannot be simply to demand less cooling, since that could cost lives. The goal has to be changing the energy supply behind it. If the world's air conditioners are powered by clean electricity power that does not rely on burning carbon, the feedback loop breaks. People could use the life-saving cooling they need without that cooling, feeding the warming that made it necessary in the first place. Follow the logic of deadly heat to its end, and it becomes one of the clearest arguments for moving to clean energy as quickly as possible, not as a distant environmental preference, but as a direct question of human survival under rising heat. A grid supplied by sun, wind, and other clean sources could provide the cooling demanded by a hotter future without further contaminating that future. In that shift, air conditioning changes roles. It stops being part of the problem and becomes, once again, only a tool of protection. The faster electricity becomes clean, the sooner the trap loosens, and the more honestly societies can rely on cooling to shield people without intensifying the underlying danger. Yet even this is not the whole answer. It would be risky to place all hope in air conditioning, even if every unit were powered cleanly, because any plan based entirely on machines remains fragile. A deeper resilience may come from reducing how much cooling those machines must provide, by changing the hot environments we have built around ourselves. Here, the news is more encouraging, because many useful responses are not exotic. Cities can be redesigned so they resist their own heat. A large part of the urban heat island effect comes from dark materials that absorb sunlight. Those surfaces can be changed. Roofs painted white or in light colors send more sunlight back toward the sky instead of taking it in, and that can noticeably cool the building below. Green roofs, covered with vegetation, cool through shade and through the evaporation of water from plants. Trees can be planted in large numbers, especially in hot, paved, low-income neighborhoods where the need is greatest. A mature canopy can lower street temperatures by several degrees through shade and the release of water vapor. Cooler pavements, parks, and water features can also help. None of this belongs to science fiction. It is architecture, landscaping, and urban planning used deliberately as public health infrastructure. Alongside that, societies can prepare for failures that are already foreseeable. Electrical grids can be strengthened and modernized so they better withstand demand peaks and storms, while distributed power and storage can reduce the chance that one failure darkens an entire region at the worst possible time. More cooling centers can be created, public, air-conditioned refuges where people can survive a heat wave even if they lack cooling at home, and systems can be built to help vulnerable people reach them. Heat, early warning systems and response plans can also be put in place, like the system France built after the catastrophe of 2003. France did take that path, and in the years since, it has dramatically reduced its heatwave death toll. That example suggests something important and practical. Preparation, warnings, and coordinated public action can save lives. The tools are not imaginary. They work when they are used. This is not a story of total powerlessness. The hazards are visible now, the physics is understood, and many of the defenses are already known, from clean energy and more intelligent urban design to stronger electrical grids and protections focused on those most at risk. The tools are not imaginary. The deeper question is how widely we choose to use them and how quickly, because that choice helps decide which future becomes real. Between the possible outcomes, the distance is vast. And that distance is what makes this moment so consequential. What makes the picture less bleak is that much of the response has already been tested outside the laboratory, in ordinary places, under extraordinary stress. France is one of the clearest examples. In 2003, roughly 15,000 people died there during a catastrophic heat event, leaving a wound large enough to change national policy. Afterward, France created a heatwave early warning system, organized plans to contact isolated elderly residents, opened cooled public spaces, and coordinated hospitals and emergency services, so that extreme heat would be treated like a recognized danger rather than a background inconvenience. Later heat waves, some of them comparable in intensity, did not produce the same scale of death. The toll fell sharply, compared with what an unprepared France endured in 2003. That matters because it is not a computer scenario or an abstract promise. It is a case in which a real country absorbed a real disaster, altered its preparation, and spared thousands of lives when dangerous heat returned. Preparedness, in that sense, is not wishful thinking. It is a proven intervention. The same pattern appears in the physical changes that make hot places more survivable, where cities have planted trees, brightened roofs, and lightened pavements. Measurements have shown cooling on the ground, sometimes by several degrees along a hot street. During a heat wave, that margin can be the space between conditions that are unbearable and conditions that can still be endured. Cooling centers have kept people alive during events that might otherwise have killed them, and grid operators that strengthened resilience and added storage have made it through demand peaks that could have overwhelmed a weaker system. No single measure erases the danger, and even together they do not remove the underlying climate trajectory we have been following. Yet they can reduce the wet bulb conditions people actually face, preserve electricity when it is most needed, and move the most vulnerable towards safety. Placed alongside a clean energy transition that breaks the feedback loop between cooling and warming, these measures could mark the difference between meeting the heat with defenses in place and meeting it exposed. The knowledge is already available. What remains uncertain is the scale of our response and the speed with which we decide to act. Part 17. 2 degrees or 4. In the end, this entire story narrows to a fork in the road, with two routes leading toward very different worlds. The numbers have already appeared, but setting them beside each other helps reveal the true scale of the choice. One path is hard, the other could be catastrophic, and importantly, the direction is not yet fully settled. Along one route is a world warmed by around 2 degrees C. This is the more hopeful outcome, though it would be misleading to call it gentle. At 2 degrees, roughly a third of the planet's land area periodically crosses the danger threshold for older adults. Much of India, populated China, and the eastern United States would fall within that zone, and a Paris-style killer heatwave would no longer be a once-a-century shock, but something arriving every few years. Such a world would demand enormous adaptation. It would strain power grids, cities, and health systems. And even with serious preparation, it would still cost lives. Yet 2 degrees is not the same as collapse. It is dangerous, but it is still a world that could be prepared for, built around, and endured with determined protection. The threat would be real, but more bounded, giving human ingenuity some room to work. The other route points toward 4 degrees. This sits at the high end of what becomes possible if emissions continue rising, or if the climate responds more sensitively than we hope. A 4 degrees world is not merely a hotter version of the first path. It is a different category of danger. More than 60% of Earth's landmass would experience these dangerous wet bulb temperatures. Conditions beyond human survivability would become a recurring feature across much of the inhabited planet. The Karachi heatwave, which in 2015 was briefly lethal for the elderly, would become lethal for the elderly almost all the time, and dangerous even for the young and physically strong. In large, heavily populated regions, there could be parts of the year when being outdoors or being indoors without reliable power becomes a death sentence. Such pressure could drive migration and disruption at a scale capable of reshaping human society, because people do not remain indefinitely in places that repeatedly threaten their lives. 4 degrees is not simply an adaptation problem. In some regions, it becomes a crisis of habitability itself, and the central point is this. The distance between those two worlds is not fixed by fate, nor dictated by physics alone. It is shaped by human decisions. It depends on how rapidly electricity moves toward clean sources, breaking the link between the energy used to cool us and the warming that makes cooling more necessary. It depends on whether cities are redesigned with seriousness, whether grids are hardened, and whether the people most exposed are protected. It depends on collective choices made over the next couple of decades, choices that help determine whether warming levels off near 2 degrees or pushes toward 4. The science is not saying that catastrophe is already sealed. It is saying that we are standing at the fork with the data in our hands, and the route remains open. That makes this warning unusual, because inside it is also an unusual form of hope. In a strange way, a fixed prophecy might be simpler, like a meteor descending while we can only watch. Then the only task would be to brace for impact. But that is not where we are. Humanity is moving toward conditions it has never lived through before. That much is true. The boundary of livability is real, and it is lower and closer than many once imagined. At the same time, we still have influence over how severe the outcome becomes. Both truths have to be held together: fear and agency, danger and choice. That balance may be the only honest way to look at what lies ahead. So the story returns to the place where it began, to the line itself, and to the meaning of being the first generation able to see it clearly. Part 18. The first generation to see the line. We began with one stark sentence. There is a temperature at which even a healthy person, resting motionless in the shade with unlimited water, will die. By the time we trace this threshold to its deepest meaning, it stops sounding like a warning phrase and begins to look like a law of the body. It is the point where the surrounding air becomes so hot and so loaded with moisture that sweat can no longer do its quiet work. At that boundary, the old cooling system built into us is effectively defeated by the atmosphere itself. Movement, instinct, and ordinary caution are no longer enough. Survival may depend on mechanical cooling, or on the air changing before the body fails. And the unsettling part is that this boundary is not where older textbooks once placed it. It appears several degrees lower, close enough to the harshest conditions Earth can already produce to make the idea feel less distant. Like a faint line drawn across a darkening sky, it also falls unevenly, most heavily on older people, the sick, the poor, and those forced to labor in the heat because stepping away is not an option. That is why the number matters. It is not abstract. It marks the place where vulnerability becomes physical. In a strange way, we may be the first generation able to see this line with any real sharpness. People before us knew lethal heat, and they grieved after the great heat waves just as we do now, but they did not have the same measurements. The controlled chamber studies involving real human bodies, or the maps that place the edge of livability across a warming planet. Those maps let us watch the risk unfold, region by region and decade by decade, showing where, and in rough terms when, the air begins to move past what the body can tolerate. That kind of sight is a difficult inheritance. It can be frightening because it removes some of the comfort of uncertainty. Yet it may also be the most useful gift available to us, because a danger hidden in the haze is almost impossible to prepare for. This one is becoming visible. What those maps reveal is not a simple ending. It is more like a branching path. One branch leads to a 2-degree world, harsher, more dangerous and demanding, but still broadly survivable. The other points toward a 4-degree world, where large portions of the inhabited planet may, from time to time, become hostile to the bodies of the people who have built their lives there. That contrast matters because it prevents the story from collapsing into despair. The maps also show something the most hopeless voices often leave unsaid. The space between those two futures is made of choices that remain open. The cleanliness of the electricity that powers cooling, the shade designed into cities, the strength of the grid, and the protection offered to people who cannot shield themselves are not fixed outcomes. Each one is still a decision in front of us. And each decision, in its own way, may shift where that line touches human life. So this is the question that has been quietly sounding beneath the whole subject. We now know there is a temperature boundary beyond which the human body cannot endure for long. We know it is real, and we have a rough sense of where it lies. We also know that a warming world is moving some of the most crowded regions toward it, including a large part of our own country within the lifetimes of people watching now. When the air crosses that threshold, the immediate protection is our ability to cool the space around us, a machine connected to a grid, drawing energy from sources we choose. In the end, then, the decisive question may not be about heat alone. It may be about what we build before the hottest days arrive. When a great city finally meets that boundary, as it will, the crucial difference will be whether the years before it were spent creating clean power, resilient electrical systems, and places of refuge, or whether we delayed until the one defense available went dark exactly when it was needed most. The heat is on its way. What it encounters when it arrives is, for now, still in human hands.